Hello, welcome to the problem session. It was a problem we did just in the last video was interference of two waves, and it's not just any two waves, but two coherent waves. These are two waves are coherent if their phase relation is not varying over time. So one way to create two coherent waves is to start from the same source, and these are wave fronts. So you can see spherical waves come out of that. I mean this source is over here, so this kind of a sphere centered about that. S0 is over there. So, and there will be another. So all these wave fronts are one wavelength apart, and when they come over here, it's the same wave front, and there is a very narrow slit here and narrow slit here. Now those narrow slits through which the wave front emerges on the other side is they are become a secondary source of wave. So this is a new source of wave, and this is another source of wave. So these are like a point sources, and they create their secondary waves. So this is not original wave anymore, but the wave created over here, and like a blue and this yellow orange wave. And so these are two sources of wave which came from the original one. So if you look at this, this wave has a wavelength lambda and a frequency f, and maybe a phase phi, which start from here, we can just set to 0 at this point. So this wave and this wave, they're in phase, and so if when they arrive over here, their relationship between the two will be independent of time. So let's look at what the wave psi1 will appear here. Psi1 at p at time t, it will be some amplitude a that came from the same and amplitude a, which can be it has gone a distance r1. So let's say it's a spherical wave, so some v over r1, so it's gone that much. That's the amplitude. And then cosine, you can write cosine k and gone distance r1 minus frequency times t. So at time t it appears right over here. This is time is t over there. And if I look at this wave psi2 at p at same time will be, because same start with same v, so it's going to be v over r2 and cosine k times r2 minus omega times t. Because the phase was 0 here, phase was 0 here, I just said it arbitrarily. If we had a phi here, then this will be phi. So it doesn't matter that I set this 0. Okay, so this is the phase here, and at p, and this is the phase of this second wave of the p. So let's call from here to here delta phase is going to be kr1 minus omega t minus kr2 minus omega t, and you can see the omega t cancelled out, and this is independent of time. When this happens, we say that these things are coherent waves. So we've created coherent waves, and so when two coherent waves come together like this, the net wave shows interference pattern, right? So net wave is psi pt, and first thing to notice here is a v over r1 and v over r2. Actually they r1, r2 and L, they're all very close together, so they're not inside the phase where nonlinear function like cosine can act, and we can replace these two by both of them v over L, and then we have a cosine k times r1 minus omega t plus cosine k times r2 minus omega t. So you can see that this is actually pretty right. This is fine. So we can write down is 2v over L. We use a cosine A plus cosine B formula. K times R1 plus R2 over 2 minus omega t. Add them and divide by 2. And then cosine k times r1 minus r2 over 2, and this is kind of independent of time because this omega t subtract cancels out over here. So so we have this, and what we observe here is place a detector, detect intensity. So you remember that intensity will be which is proportional to psi square pt time averaged. So if you look at this, this is the cosine. When I square it, I can convert it to a double angle formula, right? And it's going to become, let's call it some constant alpha, and 4v square over L square. So these are all constant, and then there is a cosine square k delta r over 2. These are all independent of time, and this is the only thing that's has a time in it. So cosine square k, let's call this average part r over 2 minus omega t. So what is the time average of this thing? So we need to do time average of this, and you can show that because this is a this is a periodic function. Let's find the period and average over one period. That will be the same as time averaging, right? So if you look at a cosine square, let's call this guy whole thing a minus omega t. That's equals to if I have two of this, then it's going to be 1 plus cosine 2a minus 2 omega t. Okay. And if you divide by 2, you're going to be like that. So when you average this guy out, this should be, average of that should be 0, right, over one period. So if I average this out, time average, so this is the part that doesn't have any time in it, so it just come out to be half. So this whole thing is 2 alpha v square over L square cosine square k delta r over 2. Now this one also I can write as a a double angle. So take the 2 out, and so this one I can 2 out and put over here. So alpha v square over L square 1 plus cosine k times delta r. Now if you look at what is k over here, so intensity is this. Intensity actually varying from position to position. So if I go over here, R1 minus R2 will be different for this point than for that point. If I go over here, R1 minus 2, so it's gonna, if I go on this point, any point on this screen, whether go this way or go over here, anywhere on the screen, there will be R1 and R2 from the 2 slits, and this is going to vary. And let me erase this and keep this, and from there we will get the formula that we used last time, okay, for interference conditions. Okay, so we had this intensity, and so this is intensity equals to this. This part, we can just call it I0 or something like that. Let's call it some constant. This is I'm just going to call it I0. So just remove that, and you can see that intensity, this can vary from plus to minus 1, plus 1 to minus 1, right? Depending on the value of this. So intensity at any point P is some constant, and 1 plus cosine, and K is, if you know K, lambda K equals to 2 pi. So they're kind of lambda and K are inverse of each other. Lambda is the wavelength. So we can write down in terms of that, K equals 2 pi delta R over lambda. Okay. So this is equal to plus 1 when, let's call this theta. No, not called theta. Let's call it beta. I'm going to call it beta here because I use the theta over there. So beta, when beta equals to 0, 2 pi, minus 2 pi, etc. So when beta equals to 2 pi n, with n equal to 0, plus minus 1, plus minus 2, etc. And it's going to be minus 1 when beta equal to pi, minus pi, 3 pi, minus 3 pi, etc. So that's equal to pi times m, and m is some odd number, plus minus 1, plus minus 3, plus minus 5, etc. Okay, so let's see. That means this will be 2I0. It actually turns out to be this I0 I just used kind of arbitrarily, right? So 2I0, if I just call it IX, because I0 has another meaning in this context, some constant IX times 2, 1 plus 1, when this 2 pi delta R over lambda equals to n times 2 pi, and n equal to 0, plus minus 1, plus minus 2, etc., all integers, and is Ix 1 minus 1 equal to 0 for 2 pi delta R over lambda equals to m times pi, and so the m's are these values. Okay, Let me erase some. So now we have our formula. See, so these are going to be maximum intensity, and this is going to be minimum intensity, and this tells us where those things will be. These are the conditions for where this will be. So found max intensity when delta R equals to n times lambda. When delta R equals to n times lambda, n equal to 0, plus minus 1, plus minus 2, plus minus 3, etc. Mean intensity when delta R equals to, when you solve this guy, you see m times lambda over 2, but m has to be all odd numbers, plus minus 3, plus minus 5, etc. So the max intensity is whether, if you're using light wave, max intensity where you will get constructive. So this will be called constructive. There will be constructive interference. And these guys will be called destructive interference. Now, there's another way to write delta R in terms of this angle. You know, from if I look at this point and I say, what's the if angle is theta, and if this point is very far away, then theta and the distance between these slits can be actually obtained, and that's what I want to show next. Okay, that's a very tricky thing to do it, and a lot of the times the textbooks, it's pretty hard to see in the textbook, but almost all textbooks have it. Let me just go over that. Okay, so I want to convert these distances, difference in distances, to the direction in which the point P is. So we have this geometry here. Geometry here is we have two slits here, and we can look some arbitrary point P over here. So we have this. This is R1 and this is R2, and this angle, the direction is theta. Now if this S1, this S2, and this distance is D, well, I submit to you that this direction, their angle and that angle are the same angle if P is very far away. If L is much greater than D, this L is much greater than this distance D, then this theta is same as theta prime. Then theta prime is almost equal to theta. And you can do it as an approximation, and you can actually nail it down when this will fail. Okay, you have to write down the you can use the trig to actually do it. I'm not going to do it because of the time. So this theta prime, and now you can actually say has to be equal to this guy over here. So this is theta prime. So this is same as that. Now imagine doing this. Okay, imagine I'm going to see, I'm going to be here, and I drew an arc. This is with a center, and this is the arc you're going to draw, and this is very big circle. So this will be almost perpendicular. Okay, so this will hit perpendicular, and so I'm using this is R1 as the smaller one as the radius when I'm drawing it, and so this is the radius I'm going to use to draw it. And so from here to here is R1, and from here to the whole thing is R2. So this little distance is delta R, and because this is a very small part of the arc, this is tangent to the arc, so this is 90 degrees over here. And so now let me redraw. This is D, and we have okay, so redrawing it, so this is delta R, this distance, and this is 90 degrees, and this was theta prime from there. So this will be 90 degrees minus theta prime because of this right angle triangle. So this will be the same angle as that. So this will become theta prime, and theta prime is same as theta in this approximation. So in this triangle, delta R will be D, this divided by D equals sine theta. So sine theta is delta R divided by D in this triangle. And so delta R is just going to be D sine theta. So in here you can call this guy D sine theta. So this will convert D sine theta. So this condition can also be written in terms of the direction in which you're looking. So this can be placed further and further out, and you just keep the same direction. So if this was the constructive, over there will be constructive. All of this will be constructive. Okay, one way you can see is if you draw it out, you're like a blue here and yellow here from the two different points. You can I've shown you one such thing is you can see if these are all constructive direction. That's the direction of constructive, because maximum of each wave kind of is coming together at the same points. So if you draw it out, you actually see a whole bunch of places there maximum appears. Okay, so in my drawing, this is the only direction I've seen, but if you draw more closely spaced waves, you're going to see a little bit more in this situation. Okay, so that's all. These are the formulas I used in the last problem, and I hope this explanation of how to convert the distance difference to the direction is very critical. That this is a far away, and we do make this assumption when we go from distance difference to the direction in which we're looking, and the angle of that, to convert that angle, to translate that angle into the angle over here, I need to make this assumption. Another thing that I would like you to kind of pay attention is that the waves have to be coherent. If the waves are not coherent, then intensity, the time averaging when you do an intensity will wash off this, and you will not see interference pattern. Okay, so it's very important that the waves are coherent for you to see the interference pattern. Okay, that's all. Take care. Bye bye.